Welcome student, Atomic Structure and Wave Mechanics, Unit 3A, General Chemistry, CH1501. I am Dr. Devang Pandya from Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Well, in our previous lecture, we have discussed the evolution of atomic theories, and in 1805 to 1924-26, between that era of time, how many scientists have contributed and what different type of atomic model they have discussed. That much discussion we have done in our previous lecture. Today we are going to discuss regarding the behavior of electron and dual nature of that particle, and the contribution of the scientist in designing the duality of the particle nature as well as wave nature of electron. Well, in this learning of the duality, first name comes that in mind is Max Ernst Ludwig Planck. That is Max Planck, well-known scientist. In 1902, he has given a theoretical research based on his study on black body radiation. The outcome he has given in a theoretical way, stating that the electromagnetic radiation, or we can say light rays, which already have a wave nature, according to Huygens and Young, should have particle nature. So in 1902, Max Planck has given this concept of duality for electromagnetic radiation, and where the electromagnetic radiation have dual character, so instead of saying the rays or electromagnetic radiation, Max Planck coined a term as quanta, a discreteness of the energy or discrete packet of energy. And for that he has given the energy equation E is equal to h nu. For this invention, he got Nobel Prize in 1918, but due to some technical issues, instead of 1918, Max Planck received his Nobel Prize 1 year later in 1990. So that was the theoretical concept, but the time was such early that people will not accept this concept of theoretical research without experimental evidence. And as a result of that, Albert Einstein, who is the very much follower of Planck, has studied Planck's theoretical concept, and based on his theoretical concept he has given experimental evidence by giving photoelectric effect, and for which he also got Nobel Prize for that. If you have gone through the autobiography of Albert Einstein, at the age of 9 years he was unable to speak his mother tongue, and at the age of 26 he won Nobel Prize for the relativity theory. So a man who is unable to speak his mother tongue got Nobel Prize at very early age, and that is why he is considered as one of the genius of that era. Albert Einstein, when has given his entrance test for diploma engineering admission, he got full marks for mathematics and physics, and for the rest subject he got 0 mark. Yet the director of that polytechnic offered him a seat to learn, and he has cleared his diploma in engineering. After completion that, he was not able to get job for himself. His father supported him, and with his reference he got a job as third category clerk in the patent office, and in patent office he accept that job only because he thought whatever new research will come for patent, that file will move from his table and he has chance to read it and learn something. And after that, you know how much deep work in physics Albert Einstein has given. So in 1902 he has taken a nickel plate and imposed a beam of electromagnetic radiation on it. He want to prove that this electromagnetic radiation, according to Planck, the word quanta is used, should have particle nature. As already have given you the example of carom. When you play carom and you will hit the striker will going to hit the object. It pass on its kinetic energy to the object and then object start moving. Because both the object and the striker in carom game made of particle, and therefore this exchange of kinetic energy is possible. So much in the same way, he incidented a photon, or we can say electromagnetic radiation, on the nickel surface. On nickel surface there should be electron arranged. So the incidental radiation which is going to collide with that electron with enough frequency known as threshold frequency, and that collision, because the incidental radiation is of having particle nature, it's pass on its kinetic energy to the electron which already have a particle nature, and that electron will eject from the surface with a flash which is known as photoelectric effect. So using that, he proved that the electromagnetic radiation which already have a wave nature, as Huygens and Young stated, should have a particle nature as well. And that way the duality is proved by experimental verification by Albert Einstein. On this concept, we found that the electromagnetic radiation have particle nature, and therefore Albert Einstein used word for photon for that. Photon is nothing else, it is electromagnetic radiation, or we can say light, and this light have dual character, wave nature as well as particle nature. Now after 20 years, in 1924, the French physicist de Broglie studied these two theories of we can say Max Planck and Albert Einstein, and on that base he has given a new concept, a new theoretical research. By comparing the energy equation given by Max Planck and Albert Einstein, he derived equation for the wavelength of a moving microscopic particle like electron, proton, neutron, hydrogen atom, kind of moving microscopic particle. But before we learn and get more information of de Broglie's contribution, let me tell you about de Broglie, which already I have briefed in my previous class. That de Broglie was a history graduate, so he learned literature, and then after he got job in military during World War 1814 to the World War end. Till that time has been in the army. During that period of time he learned science and his interest developed in science. So a history graduate, then after studied science, he done his DSc, and in his PhD thesis he put this information. Twisting the statement of Max Planck, he stated that if electromagnetic radiation, which is known as photon now, should have dual character, that means that it already have a wave nature, can behave like particle, then why not electron, proton, neutron, hydrogen atom kind of moving microscopic particle which already have a particle nature behave like wave? So keeping that thing in mind, de Broglie has given that work in his thesis. When he submitted his thesis, people disagree with his concept. They ruled out his concept and they do not accept his research work in his thesis. So de Broglie won't get disappointed. He take his thesis to Albert Einstein and told him to refer it. And after referring, Albert Einstein stated that the concept has value and his thesis is accepted, and for that work he got Nobel Prize. He is the only fellow who got Nobel Prize for a work done in his thesis. Why he got Nobel Prize? That is the application of de Broglie's matter wave. That his concept of this matter wave is used in electron microscope, which can enhance the object by 2 lakh higher pixel than its original size, on which all life science depends. All diagnosis of different disease is done possible, and that is why his research can be benefited to huge mass in the society, which earn him a Nobel Prize. So without wasting time, let's learn the dual nature of matter of electron, wave particle, nature of matter, de Broglie's concept of matter wave. According to Max Planck's quantum theory of radiation, some phenomena like photoelectric effect and black body radiation can be explained. If light radiation is supposed to behave as a material particle which is localized at a particular space, while according to Maxwell's wave theory of radiation, certain other phenomena like diffraction, interference, and polarization can be explained. If light radiation is supposed to behave as a wave which is spread out over space, thus we find that light shows dual character. It behaves both as material particle and as a wave. So in 1924, this French physicist Louis de Broglie extended the idea of Dunk character of light to matter particles. Particles like proton, electron, neutron, hydrogen atom, or that kind of moving microscopic particle, and suggested that all matter particles in motion like electron, proton, neutron, hydrogen atom, or any molecule which we cannot see through naked eye have a dual character. All matter particles possess characteristic of both material particle and a wave. The wave associated with matter particles is called de Broglie's matter wave. This revolutionary idea proposed by de Broglie that a material object possesses both particle and a wave properties is known as the wave-particle duality in matter. This idea of wave-particle duality in matter led de Broglie to a very important conclusion that since an electron is also kind of matter particle, it also like matter particle has a dual character. An electron, like all other matter particles, behaves both as a material particle and as a wave. Now the difference between the de Broglie's matter waves and electromagnetic waves. The main difference, 3 differences are there. First, de Broglie's matter wave are not radiated into empty space or emitted by oscillating particles. For example, they are never dissociated from the particle but remain attached to the particle. On the other hand, the electromagnetic waves like rays, like photon, can be absorbed or emitted. Number 2. De Broglie's matter waves travel with speed which depends on the nature of the matter particles, while electromagnetic waves proceed with the speed of light. And the third difference is de Broglie's matter waves are not electromagnetic in nature. So these are the differences between the matter waves and photon. Now de Broglie's equation, with the help of Planck equation where E is equal to energy of the quanta is equal to h nu, when nu is the frequency, and Einstein's mass energy relationship E is equal to mc square, where E is considered as energy of photon, h is the Planck constant, and nu is the frequency of the radiation or electromagnetic radiation or light of photon. M is the mass of photon and c is the velocity of light. De Broglie derived a mathematical equation which gives the magnitude of wavelength lambda of a moving electron in terms of its mass and velocity. This equation is lambda is equal to h by mv. This equation is called de Broglie's equation and the wavelength lambda is called de Broglie's wavelength. Since the product of m into v, that is mv, is called the momentum of a moving electron, the above equation can also be written as de Broglie's wavelength lambda is equal to Planck constant h upon momentum of electron mv. The equation shows that since h is constant of proportionality, the momentum of moving electrons, that is mv, is inversely proportional to its wavelength lambda. These are the small things which you need to keep into mind as far as MCQ exam is concerned. Derivation of de Broglie's equation. We have seen that energy of a photon, that is E, is related to its frequency nu by Planck equation, which is given as E is equal to h nu, or E is equal to hc by lambda, where nu is equal to c by lambda, that is the frequency. Here lambda is the wavelength of the radiation and c is the velocity of the light. Again, the energy of a photon E with mass m and velocity c is also given by Einstein mass energy relationship as E is equal to mc square. That is Einstein's mass energy relationship. Let us label it by equation 2 and this one is equation 1. So equating the equation 1 and 2, we get hc by lambda is equal to mc square. Means h by lambda is equal to mc or lambda is equal to h by mc. And because this is related to photon, here the velocity is indicated as c. If the above equation is applied to a moving electron of a mass m and moving with a velocity v, then the above equation can be reduced to de Broglie's equation, that is lambda is equal to h by mv. And this is de Broglie's equation which gives the value of wavelength lambda of a moving electron in terms of its mass and velocity v. Now here you can see that from photoelectric effect we will get this value, and this is Einstein's equation, and we can get that value of the momentum from here, and using these two information we can reach to the value of lambda is equal to h by mv. Now de Broglie's equation as applied to large and small particle in motion. Limitations of de Broglie's equation. So what is the limitation of de Broglie's equation? We can, if somebody will ask, you can mention this part. Whether de Broglie's equation is applicable to large particles like stone, like earth or planet, or some small particles such as electron, proton, neutron, hydrogen atom, can be known by calculating the magnitude of de Broglie's wavelengths for these particles and then comprising them. The wavelength of large particles and B part also. So we will going to discuss the wavelength of a large particle over here. Let us consider a large particle like a stone or an earth or an elephant or any big object of a mass 1. Suppose we have been considering here stone of a mass 1 gram, that is 1 into 10 raised to minus 3 kilogram, moving with a velocity that is equal to 1 meter per second. Then lambda is equal to h by mv is equal to 6.624 into 10 raised to minus 34. This is a typological mistake. You need to consider minus 34 divided by 1 into 10 raised to minus 3 into 1 meter, and that is equal to 6.624 into 10 raised to minus 31 meter. This value of lambda is shorter than the wavelength of an electron magnetic radiation, photon, except cosmic rays, and hence cannot be measured by any conceivable method. Thus, de Broglie's equation has no significance for large particle like stone, elephant, moving aeroplane in the space, or moving planet in the universe. On the other hand, if we have a wavelength of a small particle, let us consider as an electron in a hydrogen atom with mass 9.108 into 10 raised to minus 31 kg and moving with a velocity 2.118 into 10 raised to 6 meter per second. Then lambda is equal to h by mv is equal to 6.624 into 10 raised to minus 34 divided by 9.108 into 10 raised to minus 31 into 2.118 into 10 raised to 6 m is equal to 0.3323 into 10 raised to minus 9 meter. This value of lambda is quite large and comparable to the wavelength of X-rays and hence can be measured. As may be seen from the above calculation, de Broglie's matter wavelength of large particle in motion is very small and hence cannot be measured with the same of the small particle is large enough and hence can be measured. So this is the comparison with the big object and a small moving microscopic particle. Thus we find that de Broglie's equation is applicable only for small particle or moving microscopic particle like electron, proton, neutron, hydrogen atom, molecule, etc., which we cannot see through naked eye, and has no significance for large particle or macro size particle like stone, elephant, car, planet, etc. Now, based on de Broglie's postulate, I will going to give you these two problems to solve out yourself. This is work from home. One is calculate the wavelength of a body of mass 1 milligram moving with velocity of 3 meter second inverse, where the Planck constant value is already given, that is 6.624 into 10 raised to minus 34 joule second. And the other example is in SI unit you need to calculate. Applying de Broglie's equation, calculate the wavelength associated with the motion of an earth, a stone and an electron. The mass of and the velocity of this object is already given. Earth has mass 6 into 10 raised to minus 24 kilogram with velocity 3 into 10 raised to 4 meter second inverse, and stone has 0.1 kg mass with 1.0 meter second inverse velocity, and electron has 10 raised to minus 30 kilogram mass with 6 into 10 raised to 5 meter second inverse velocity. Planck constant here you need to take is 6.6 into 10 raised to minus 34 joule second. Do not take 6.626. 6.6 into 10 raised to minus 34 joule second, that you need to consider as Planck constant for this problem. So that two problems I would like to give you to do it from the home. If you have any doubt, problem and question and queries, feel free to ask anything. Then after in 1927, when the de Broglie's hypothesis, which is a theoretical research, hasn't got any experimental evidence, then two scientists, CJ Division and Alej Gamma, give this experiment. They have taken a nickel crystal much in the same way as Albert Einstein has taken a nickel sheet and imposed a beam of electromagnetic radiation, that is photon. Instead, this CJ Division and Alej Gamma has used electron gun and imposed a beam of electron on the nickel surface. And to prove the wave nature of anything, say with the 50 degree of the rotation of imposing radiation, they found this kind of curvature which indicates that electron should have a wave nature. So that wave nature has been proved, or in other sense we can say that when the electron gun imposed a beam of electron on nickel crystal, they found diffraction. That is one of the property to establish the wave nature of an electron. So to give the wave nature of electrons, CJ Division and Alej Gamma give this experimental verification to de Broglie's postulate. Since it is not there in the syllabus, I haven't described much more. Just you need to understand that the experimental verification is given by CJ Division and Alej Gamma using the same concept as Albert Einstein has done. They have taken a nickel crystal instead of nickel plate and imposed a beam of electron instead of a beam of radiation, and by moving this, getting the angle of 50 degree, they got this kind of wave. They got this kind of waves for the electron and got the wavelength for the electron, and on the base of that they proved the statement of de Broglie's postulate, that the electron, proton, hydrogen atom, neutron kind of moving microscopic particle which already have a particle nature can behave like wave. Experimental verification of de Broglie's matter wave given by CJ Division and Alej Gamma's experiment. Please see that experiment.
In 1924, Louis de Broglie postulated that all forms of matter have both wave and particle characteristics. According to this hypothesis, electrons, just like light, have a dual particle wave nature. Two American physicists, C.J. Davison and L.H. Germer, were the first to experimentally prove the wave nature of material particles in 1927. Displayed here is a block diagram of the experimental setup used by Davison and Germer. It consisted of a nickel chloride crystal, the target, an electron gun, G, and a detector. The electron gun produced a beam of electrons. The electron gun used by them consisted of a tungsten filament, F, and high and low tension batteries. The low tension battery was used to heat the filament. The red hot filament produced an electron beam. A high tension battery was provided to accelerate the electron beam. The detector or the electron collector moved on a graduated circular scale. A sensitive galvanometer was also connected to the detector. How did they perform the experiment? The electron beam was made to pass through a pinhole and made to strike the crystal normally. The electrons scattered in all directions, acting like waves. They observed that at certain angles, the detector indicated a peak in the intensity of the scattered electron beam. This maximum intensity was due to constructive interference, a phenomenon confined only to waves. Thus, they experimentally proved the wave nature of electrons. Davison and Germer plotted a graph taking the angle between the incident and scattered direction of the electron beam, phi, along the y-axis and the intensity of the scattered beam at different values of accelerated potentials along the x-axis. The nature of the graph is shown here. From the experimental curves obtained, the following conclusions were drawn. Intensity of scattering depends upon the angle of scattering, phi. A bump or kink always occurs in the curve when phi is equal to 50 degrees. This bump or kink increases as the accelerating potential difference is increased. At 54 volts, this bump is maximum, and then it decreases on further increase of potential difference. This peak indicated the wave behavior of the electrons. Thus, Davison-Germer experiment verifies de Broglie's hypothesis of wave nature of matter particles.